Hi, and welcome back to another extreme value theory video. In the previous video, we considered how when we have a positive shape parameter for our extreme value distribution, we can make a simplifying assumption and use what's known as a Hill estimator to simplify our extreme value analysis. In this video, what we're going to consider is how we can adapt our standard extreme value analysis process that we've seen building up in the first 4 weeks of the course in order to estimate some financial metrics that are of particular interest. So when we're operating in a financial or an actuarial setting, there's certain quantities that are of particular interest to, for example, an insurer or a reinsurer. The first of these is the value at risk, which is essentially a quantile of the distribution of your process, and the expected shortfall, which is essentially a conditional expectation where you're conditioning on your event being large. So this is of particular interest in an actuarial setting where you might be trying to work out what sort of size payment you're going to have to make, given that you're making a large payment. So in this video, what we're going to do is consider each of our previous models that we've considered so far in the course and see how to calculate these two quantities in those settings. We're also going to look at how we can incorporate a little bit extra into this by allowing for the volatility and level of our process to change over time. So to begin, we'll consider the case where we have IID observations underlying some block maxima. So we're going to be fitting a GEV distribution. And I'll just get rid of that. So if we're going to be estimating the value at risk, we're going to need a quick refresher of what is meant by the value at risk. So the value at risk with probability P is going to be the value where our underlying process is less than that value with probability 1 minus P. Notice that this is exactly the definition of a P quantile of the distribution function of X. If we are basing our analysis on a set of block maxima where we have M blocks, each of length N, then what we can do to estimate the value at risk is simply to consider the appropriate quantile of the fitted GEV distribution. So since this GEV is going to be approximately f of x to the n, to estimate a quantile of f of x, then we're going to want to incorporate a power of 1 over n into our GEV density here. And that's exactly what we've done to work out this quantile, which is just going to be given by mu plus sigma over psi times 1 minus n log 1 minus p, all to the minus psi. So all this is a particular quantile of this GEV distribution. If we want to obtain a point estimate for the value at risk, we can do that by substituting in the MLE that we've found for our GEV parameter estimates. So plugging in mu hat, sigma hat, and psi hat into this expression. And if we want to express the uncertainty in our estimate of the value at risk, we can do that using several different methods. Firstly, what we could use is the delta method. Secondly, we could construct a profile log likelihood for the value at risk in much the same way as we did for a return level in the previous sections of the notes. Or what we could also use is a simple bootstrap in order to resample our block maxima and construct the sampling variability of this quantity. So moving on now to the case where we want to estimate the value at risk, but we have threshold exceedance data that is IID. In this case, what we have, by the very nature of our modelling, is an excellent expression for conditional quantiles being given simply by the GPD density itself. So the probability that x is greater than a little x, given that it's greater than some high threshold u, is going to be given by the GPD density here. What we're interested in with the value at risk is not a conditional quantile, conditional on being large, but just a marginal quantile here. So what we have to do is undo the conditioning in this expression. And that's very simple to do. To get the probability that x is greater than little x, that's simply going to be our conditional probability that we had before, given by the GPD density function, multiplied by the probability that x is greater than u, which, as we saw earlier, can be estimated using the sample proportion of exceedances, or if this is non-stationary, we can fit a more complex model here. But since we're in the IID case, we can use the simple point estimate of the sample proportion here for phi u. In order to get our expression for the value at risk, which is just a particular quantile of this random variable x, all we have to do is rearrange this survivor function in order to obtain the correct quantile. And doing so, we find that the value at risk is given by the threshold plus sigma u over psi times phi u divided by p to the sigma minus 1. So here we have an expression where, again, we can plug in our point estimates for our parameter values, sigma u, psi, and phi u, to obtain a point estimate of the value at risk. And those same three methods can be used again to construct a confidence interval for our estimate. So as a reminder, those methods were using the delta method, because we just have a function of our other estimated parameters, a profile likelihood, and doing a simple bootstrap procedure to resample the size of our threshold exceedances. Moving on now, beyond the case of IID data, we saw that in section 5.3 of the notes, if we have a GeV fitted to a stationary process with extremal index theta, then the GeV fitted to the stationary process is going to be approximately equal to the density, the CDF of our underlying process, raised to the power n times by theta. So here we are following a very similar procedure to what we had before, apart from we now incorporate the extremal index into our calculation of the value at risk. So this gives a very similar expression to what we had before, but it should be noted here that if we just have the block maxima available to us, then we can't perform this type of analysis. And the reason for that is that in order to estimate theta using the runs method, we need all of our data available to us, not just the maximum within a certain period. So what we can see from this expression is that if we were to ignore dependence and assume that theta was equal to 1, when in fact we don't have independent observations, then what we're going to do is overestimate the effective number of independent observations per block, and that's going to lead us to underestimate the value at risk. So it's going to put us in danger of thinking that we are at a lower risk than we actually are, so that we're thinking we're less exposed than we actually are. If we're looking at a stationary data case but using a GPD, we can use runs declustering in that setting and estimate the GPD parameters based on the cluster maxima. We can then plug in our estimates based on the cluster maxima to our previous expression for the value at risk, and that's still going to be perfectly valid. But in order to calculate standard errors for either the GeV or the GPD case, we're going to require block bootstrap estimation of those standard errors. So we're going to have to resample blocks of exceedances. Sorry, clusters of exceedances. So moving on to our second metric now, we're going to consider the expected shortfall, which is also known as the conditional value at risk. What this quantity gives us is the expected negative return, so the expected size of our loss, given that the value at risk has been exceeded. So if we know we're in a big loss situation, how big is our loss going to be? And this is exactly a conditional expectation, where the conditional distribution is of x, given that x is greater than the value at risk. If we fitted a GPD model, then what we have is a very natural way of estimating this, because we know that if our threshold u is less than the value at risk that we're considering, then threshold exceedances of the value at risk are also going to follow a GPD. And so this is what's given in this expression. The exceedances of the value at risk, given that x is bigger than the value, so this second term here should be greater than u, is following a, so just to clarify, sorry, this first expression should be x minus the value at risk, given x is greater than u, follows a generalized Pareto distribution with parameters sigma u plus psi times the value at risk minus u. So this is our sigma parameter at the value at risk. And our shape parameter, as always, is going to stay constant and just be psi. What this means is that when we have a psi value less than 1, the expectation of this GPD is going to exist, and our expected shortfall is simply going to be our value at risk plus the expected exceedance size of the value at risk, which is given by this second term in the expression. And note that it's important here that psi is less than 1, so that this expectation is finite. Otherwise, our expected shortfall is going to be infinite. Finally, we'll move on to start addressing how we can use these techniques in a more realistic data setting. So in genuine financial data sets, it's very often the case that you're not going to have stationary or IID data. The level and volatility of your process is going to be changing over time. In order to cope with this, what we can do is use an idea very similar to the pre-processing that we saw in previous chapters, but a slightly simpler version. What we can do is make a local estimate of the mean level and the volatility of a process, so the variance of each observation, and then we can filter our process in such a way to render our filtered process approximately stationary. So the way we do this is using a smoothed or window-based estimator to get an idea of the local value of our mean and variance. So this could be, for example, taking the mean and variance of the previous 20 observations or the 11 observations centered on our observation. Or if we're using a smoothing approach, weighting each observation by its distance in time from the observation that we're interested in. Once we've got an idea of the local mean and the local variance at each observation, what we can do is construct a secondary process, which we're going to call Z. And we're going to do that by taking off the mean of the process at that time and dividing by the estimated standard deviation at that time, where the tildes here are showing that we've got a smoothed estimator. What this is going to do is have a process Z with approximately 0 mean and unit variance, and it's going to remove any trends from our data as we're doing that. What we can then do is assume that this process Z is stationary and use all of our usual modeling techniques on that process instead. That gives us a much better justification for fitting a stationary model than if we were to look at the raw X process, because at least we know that the first 2 moments are approximately constant over time. So once we've fitted our standard models that we've seen in the first 4 weeks of the course to the ZT process, we can then estimate the quantities that we're interested in for Z and then back transform those onto the X scale to get our results on the scale that we're actually interested in. So for example, if we've got our filtered process Z and we've estimated its value at risk, and notice here that this isn't going to be a function of time because we've made the assumption that our process is stationary. If we want to map that back onto a particular time in the X process, so we're interested in the value risk for X values at time t with probability p, then what we're going to do is find the value at risk with probability p in the Z process, then multiply that by the estimated local standard deviation at time t, and add on the mean level at time t. A very similar process can be used in order to estimate the value, not the value at risk, the expected shortfall on the Z scale as well. Great, so that's everything I had to cover in this video. What we've seen is how we can describe financial quantities of interest, or two in particular, that are linked very strongly to the extreme value models that we've been encountering in the first 4 weeks of the course. In the next video, what we're going to do is move on and start to look a little bit at how we can look at extremes of more than one random variable and how we can describe the dependence between those random variables at extremal levels. Thank you very much for your time, and I'll see you in the next video.